Next up, top stereotactic and functional neurosurgery abstract presented by Matthew Luchette, incorporating newly learned with established information within the prefrontal cortical network.
Hey everyone, I'm Matt. I'm a resident at Boston Children's, and I'm going to talk about some work I've done in Ziv Williams' lab on learning integration in the prefrontal cortex. To start off, what do I mean by learning integration? So learning integration is the process of incorporating new information into what you already know. So the analogy I like to use is in calculus, when you learn the concept of derivative, you have to rely on the concept of the slope that you learned in algebra. So the slope would be the novel learning, and then the derivative would be the integration. So just some background information. So we have an understanding that learning integration is a unique entity from novel learning itself, from this concept of mental schemas. So we know that the rate of integration is faster than the rate of novel learning. And the prefrontal cortex in particular is important in learning. So we know that it has a role in working memory, rule representation, and associative learning. And then there's two regions in particular that we focused on this study, the dorsolateral prefrontal cortex and the ventrolateral prefrontal cortex. We know that the dorsolateral is important for utilizing rules to select responses, and the ventrolateral is important in response inhibition. So how did we do the integration in the study? So we focused on macaques, and we designed learning sets where two-step learning sets where monkeys would learn a base association. So in this case, it would be B is greater than C, and that's considered the initial learning. And then after that, they would learn two different types of integration associations. So the first type was when the association actually integrated to what they previously learned. So for instance, A is greater than B or C is greater than D builds on that initial stem. Or they learned something entirely new. So D is greater than E, which doesn't build on the initial stem. So this is just an example of how those learning sets would look. They would learn first the stem association, B is greater than C, and then subsequently they would learn one of the stems. So the first thing we found is that the dorsolateral and ventrolateral prefrontal cortex have a different signature in their expression of theta power. So if we look at these two graphs where the y-axis is showing the change in theta power and the x-axis is showing the subsequent trials in the learning set, we can see that the ventrolateral prefrontal cortex has a peak around where learning criterion is reached, whereas the dorsolateral prefrontal cortex shows an overall decrease in power as the learning set progresses. So the ventrolateral prefrontal cortex seems to be more associated with the learning rate, where the dorsolateral prefrontal cortex seems to be associated with the learning process itself. And this is just a bar graph to show the same thing. So if we look at the ventrolateral prefrontal cortex for the change in theta power and each of the three learning stem types, you can see that there's no huge overall change in theta power in the ventrolateral prefrontal cortex from the beginning to the end of the learning set. But there is an overall increase in theta power for the integration trials and a decrease for both the initial stem and no integration learning sets. And then finally, and perhaps most interestingly, is if we look at the coherence between the two regions for the three learning association types, we can see that there's a decrease in ventrolateral and dorsolateral prefrontal cortex coherence for the initial stem and for no integration if you look at the blue graph on the right. But interestingly, there's an increase in the coherence for integration sets, as shown by the red graph on the right. So these are some of my references. Thank you so much.